Welcome to this podcast on the equations of planes. In class, we covered two examples. The first example looked at determining the equation of a plane given 3 points. The second example then looked at finding the equation of a plane using a line that was in the plane as well as a point. And this example goes a step further, and now we're going to be given a point in a plane as well as the plane that we're searching for being parallel to the YZ plane. And also we need to determine the coordinates of one other point in the plane that we find. So prior to beginning, let's just recall that the equation for the plane, or any plane in general, so call it plane P, is going to be equal to, the components x, y, z equal to x naught, y naught, z naught, plus scalar multiples of direction vectors a and b. Okay, so we'll use the parameter s to denote scalar multiple of a1, a2, a3, and to that we're going to add multiple of the vector b with components b1, b2, and b3. Now, as you can see, we already have the point x naught, y naught, z naught. It's provided in the problem. So 2, 1, and minus 3 will be placed here. Now, as for the components to the vectors that we need, they're just not there. So we need to come up with these. Now, the secret lies in this fact here that the plane we're searching for is parallel to the YZ plane. Okay, so these components here are going to be those two vectors that define, in general, the YZ plane. So that's exactly what we need to do. So what I thought we might want to try, works better with technology, but what we could do is prepare a sketch. So here's our YZ plane. Okay, so I'm just going to label that as YZ. Okay, and of course the x-axis, we'll put that in as well. I'm just going to use a trend line in this case because x really isn't a concern for us in terms of the YZ plane. In fact, for the YZ plane, the x component would be 0. So we can go back and fill this portion in here. Okay, so those should both be zeros. So the YZ plane, I'm just going to box this in, and again we're disregarding x for the time being. So let's just put a rectangle around this. So really we're looking at this surface here, okay, going through the origin. This would be our YZ plane. Okay, I'm just going to shade that in as well. Just a little bit of color to it, nothing too dark. And oops, my apologies, it's not what I want to do. There, that's better. Okay, and we're just going to send that to the back so we can see the axes. Okay, so there you have it. The point that's in question, 2, 1, minus 3, if we have, take a quick look at where that would be. So we come 2 out on the positive x-axis, that's here. We'll head over 1 to the right on the positive y-axis, that would be in this direction here. And then we'll drop 3 units on the negative z-axis. So you can scale it in any way you like, but let's just say for your argument's sake that the point is here. Okay? This point is in front of the YZ plane. Okay, and you can see that because of the x component being a positive 2. So just to kind of make that a little more clear, what we can also do is take this uh, diagram and we can more or less spin it, okay, so that it's facing, that is the y-axis is pointing out of the page. So again, let's try this. So let's draw in, this will be our z-axis, okay, and then the intersection of the y and the z would be, you know, in here, but the y-axis would be jutting out of the page, okay, and the point that we're after would be just here, that is just underneath the y-axis, okay. So the reason why I show you these things is that so we can get a visualization on the problem, and maybe through that visualization we come up with a solution. Now the only thing that we could possibly have going for us in terms of the YZ plane is the fact that itself reference to the origin, and that is here, okay. We could use basis vectors. So recall the basis vectors I, j, and k. So a basis vector for the y direction or y component. So if you just want to draw out a basis or unit vector here, and in the y direction that would be j hat. Okay, and then the components, of course, of j hat, that is at the end here, are 0, 1, 0. Okay, that's a very poor looking j hat, so I'm going to try to redraw that. There, that's much better. Okay. And then also to define any other vector in the space of yz, or what we say spans all of yz, we would use a basis vector k, or k hat, okay, of unit length, which would have components 0, 0, 1. Okay, so what that means is that as we spin, right, as we take this directionality here, as we turn the y-axis out, what you'll notice is that we have basis vector k going this way, or k hat, and then we will also have, I'm just going to move this blue point, okay, so let's just say that the y, or j hat, is now coming out of the page this way. And I'm just going to put this point back in, slightly different location, but just relative to where we think it needs to be. So for the sake of the example, we'll just place it there and say that that's where it was. So at this point in time, what we need to ask ourselves is, do we have two direction vectors that we can draw from this point, okay, which is 2, 1, minus 3, such that we can define the entire plane using them? The answer to that is an absolute yes. Okay, so we won't necessarily be using just j and k, but in this case, we're definitely going to have to scale those particular vectors. So at this point in time, what we could do is we could translate those vectors. Okay, so they're non-collinear, but they are parallel to the yz plane. So we simply take these vectors. I'm just going to move these out of the way. Okay, just put this here. Take that out. Bring j back in. So those direction vectors could be used to define the yz plane. The only thing is that for the plane itself, we can't just use the basis vectors. We need to scale them. So this is where the parameters s and t come in. So let's now say that these are not of unit length, but we have sk, and here we have tj. So we're scaling them out. And of course their components, in this case, would be S is going to scale the components 0, 0, 1, that's in the Z direction, and Tj, T is going to scale out J, such that we have T being multiplied onto 0, 1, 0. Okay, so through the linear combination of those values, we therefore are able to define the YZ plane. Now to finish the problem off, recall that we do have to add on a vector that comes from the origin, and in this case that vector, let's say the origin is here and moving out to that point there, okay, that would be the vector r naught that we had seen earlier in the lesson. So the sum of r naught along with scalar multiples of the direction vectors produce the vector r, which we saw in a previous example, which defines the plane. So now we can go back, okay? You can spend more time sketching this out, and I definitely would recommend that you do try to make connections to an earlier part of the lesson, but we are simply going to scale these vectors here by S and T, and we have an equation for the plane. Last but not least, it does ask to determine the coordinates of one other point in the plane, and that is a very simple task to do. S and T belonging to the real numbers, we simply need to select any value of S and T. Okay, so why don't we take some values that are very easy to use? Okay, so we could set either value, at least one of them to 0. We can't set both to 0 because we would then have nothing more than the original point. So if we set S to 0 and T to 1, right, then X, Y, Z would map onto, and here's the formula that allows us to complete the mapping. So we would have 2, 1, minus 3, and we're going to add on the 0 multiplied by 0, 1, 0, which of course is going to be nothing more than 0, and then 1 multiplied by 0, 0, 1. So what we're going to see here is 2, 1, minus 3. Of course, this here is going to be a 0, and over here we have 0, 0, 1. Adding the components of those vectors together, we end up with, or sorry, not vectors, but points. We have 2, 1, and minus 2. Okay? So therefore, when S equals 0 and T equals 1, we have X, Y, Z being equal to 2, 1, minus 2. Okay? So there's an example involving finding the equation of a plane that is parallel to another plane. Okay? An extension to this would be to look at the equation of a plane that's perpendicular to the one that's given, but that'll come out in a later lesson. Last but not least, and we'll check our time, we're up to 13 minutes. This one here, let's try to keep this well under 20. So we'll determine if the point 8, 4, minus 7 lies in the plane that is defined by these parametric equations. The way we proceed with this is that given the point 8, 4, 7, okay, what we then have is we can broaden the definition by substituting in the values. So let's go ahead and do that. Oops, that should be minus 7. So minus 7 is equal to minus 2 plus 2s minus 3t. Now what we want to do at this point in time is we would like to clean this up a little bit. Okay, so let's tidy up, and we'll simply remove the constant from the right hand side and bring it to the left. So we'll have 7 equal to 2s plus t. Let's call that equation 1. Bring the 4 over to the left, so we have 4 equals minus s plus t. Let's call that equation 2. And then equation 3, bring the minus 2 over, we'd have minus 5 equals 2s minus 3t, and that's equation 3. So you're probably remarking that we now have a system of linear equations in 2 variables. In fact, we have 3 equations, all of them in 2 variables. What we'll do is, through a process of either substitution or elimination, we will focus on utilizing, let's get some highlighter here, equations 2 and 1. We'll solve for s and t using those. So what you should note is that if you take a look at the coefficients of our t terms there, if we do perform a difference between 2 equations, let's say 1 and 2, so we'll perform 1 minus 2, which will bring us to our 4th equation. 7 less 1 is 6. 2s minus s. Watch the double negative on this one here. It becomes a plus s. So we'll have 3s here. And then the t's, when upon subtraction, will cancel. So we're left with a solution of 2 equals s. Okay, so let's call this. This will be our number 4 in terms of an answer. So let's set the value for s into either 1 or 2. So let's go with 2. It seems to be relatively easier looking to work with. So 1 will be equal to 2 plus t, right? So we substitute 2 in for s, and that should be minus 2. Okay, if we reconsider the change that I had made there, so minus 2 plus t equals 1. And if we solve for t, we're going to get a 3. Okay, so if s is 2, t is 3, what that means is if we substitute these 2 values into the 3rd equation, okay, so if we take this value and this value here, we bring them back in for s and t. If it turns out that we end up with a solution of minus 5, then that means that the point right here, 8, 4 minus 7, is on the plane because it is able to satisfy each of the parametric equations given the values of s and t. So let's go ahead and do a substitution. So that is for equation or statement 3 with s equal 2 and t equal 3. Our left side, I believe, was negative 5. And our right side is going to be 2s, okay, minus 3t, which would be 2 by 2 minus 3 by 3, which is 4 minus 9, which gives us minus 5. So since the left side is equivalent to the right-hand side, this entire process then helps us to say and or conclude that 8, 4 minus 7 is a point on the plane P, which is defined by the parametric equations that were given here at the onset of the problem.